Louis de
is recognized as one of the key figures in the history of quantum mechanics. Unfortunately,
Let me ask you something new. What if I told you that you, me, your pet cat or dog, and even the flying shuttlecock that you smash in your badminton games are all waving and they move in any direction? Not waving low, but actually behaving like this. Sounds bizarre and unrealistic, doesn't it? Well, welcome to quantum physics, the study of matter and energy behavior at the smallest scales, like atoms and subatomic particles. Back in 1924, a guy named Louis de Broglie asked a mind-blowing question. If light can act like particles, could particles act like waves? Sounds well, right? But this idea wasn't totally random. Just a few years earlier, in 1905, Albert Einstein had already rocked the science world with the photoelectric effect. He showed that light, which we used to think of just as a waves, could also act like particles, little packets of energy called photons. This discovery earned Einstein the Nobel Prize, and it proved that light isn't just a wave. It can both a wave and a particle. The wave-particle duality of light. So the Broglie thought, hey, if waves like light can act like particles, why not flip the script? What if particles like electrons could act like waves too? And boom, they flipped the science world upside down. That idea became the Broglie wavelength, and it's a key part of quantum mechanics today. In this video, we will break it down. We will do a quick calculation and see why this wavelength even matters. Basic idea is, in quantum physics, tiny particles like electrons, protons, and even atoms don't just travel in straight lines. They also act like waves depending on how fast and light they are. This means every moving particle has a wavelength, a bit like ripples in water. And de Broglie gave us a simple formula to calculate it. Lambda is equals to h over rho, wherein lambda is the wavelength, h is Planck constant, that is about 6.626 times 10 raised to negative 34 joules second, or 4.14 times 10 raised to negative 15 electron volts seconds. Rho is the momentum, which is equal to mass multiplied by velocity, or c. Now let's solve a problem. So now let's say we've got an electron zooming around at 2.77 times 10 raised to 6 meter per second. What is its de Broglie wavelength? First, let us write the given in this problem. So for Planck's constant, we have 6.628 times 10 raised to negative 34 joules second. And for the mass of the electron, we have 9.11 times 10 raised to negative 31 kilograms. And the given here in this problem is the velocity or the speed of electrons. So we have 2.77 times 10 raised to 6 meter per second. And so the formula, we have lambda is equal to Planck's constant over rho, or the momentum. But here, since only the velocity or the speed is given, we'll solve it using the formula. So plugging in here, the given, we have lambda is equal to 6.628 times 10 raised to negative 34 joules second, divided by the mass and velocity of 11 times 10 raised to negative 31 kilogram, and the velocity of the electron, which is 2.77 times 10 raised to 6. Insert first the thing. So we need to solve first the denominator because we are following the PHYS rule. So lambda 6.626 times 10 is negative 10. And solving the denominator, we have 2.3548 times 10 is raised to negative 10 kilogram meter per second. Here, take note of the cancellation of units, as joule is equal to kilogram, meter squared, second squared, so we cancel the same units. So the remaining unit will be meter, which is the unit for wavelength. So solving it, we have 6.626 times 10 raised to negative 34 times 2.515 point of negative 10 supposed to 2.626 times 10 raised to negative 10. So the wavelength here is 2.626 times 10 raised to negative 10. So the unit here is meter. The Broglie wavelength of this problem is 2.626 times 10 raised to negative 10 meters. That is about the size of a single atom. Now, why this matters? This de Broglie idea gave birth to things like electron microscope, which let us zoom in and see things way smaller than light microscope can, like atoms. And it's not just for science geeks. This wave idea helps run stuff like semiconductors, quantum computers, and even lasers. Without de Broglie's idea, modern technology would still be in dark ages. So to sum it up, tiny particles behave like waves, and de Broglie figured out how to measure those waves. This helps us understand how atoms work and builds the foundation of quantum mechanics. Thanks for hanging out in this mini crash course on the de Broglie wavelength. Hope it made your brain wave a little. Bye!